A warm greetings to one and all. In this session, let's learn about Alpha Beta Pruning Algorithm with a solved example problem. Alpha Beta Pruning Algorithm is an optimization technique for mini-max algorithm in game playing AI. It uses two-player games like chess, tic-tac-toe, and checkers. It helps in reducing the number of nodes evaluated in the search tree. The number of nodes to be visited by mini-max algorithm are exponential, which shoot up the time complexity. The minimax algorithm explores all possible moves, but this can be computationally expensive. Some of the branches of the decision tree are useless, and the same result can be achieved if they were never visited. Therefore, alpha beta pruning cuts off these useless branches and the best cases cut back the exponent to half. Alpha beta pruning eliminates unnecessary branches without affecting the final decision and reduces the time complexity. Let's break down the alpha beta pruning algorithm. So this involves two threshold parameters, namely alpha and beta for future expansion. So it is called as alpha beta pruning algorithm. The two parameters can be defined as the alpha, the best choice, that is the highest value we have found so far at any point along the path of maximizer. Here the initial value of alpha is always minus infinity. The max player will only update the value of alpha. Beta is the best choice, that is the lowest value we have found so far at any point along the path of minimizer. The initial value of beta is plus infinity. The minimum player will only update the value of beta. While backtracking the tree, the node values will be passed to upper nodes instead of values of alpha and beta. We will only pass the alpha and beta values to the child nodes. The condition used by alpha beta pruning is to prune the useless branches is alpha greater than or equivalent to beta. So this is one of the important condition which we have to check in this algorithm. In the best case, it reduces the search space by half, improving the efficiency. It makes AI faster and more efficient in decision making. Let's solve an example problem now. Here, the root node A is always max initialized with the value minus infinity because it represents the decision-making entity, that is AI or main player. It tries to get the highest possible outcome. Next, minimum. It represents the opponent, that is node B and node C. It is initialized by infinity. It tries to respond by choosing the worst outcome for max player. Next, the node D, E, F and G represents the max player and initialized by the value minus infinity. This alteration continues through the game tree until the final decision is made. Now we need to expand the game tree from root node A using DFS algorithm till we reach the leaf node. Node A value is initialized with alpha is equivalent to minus infinity and beta is equivalent to infinity. Now we move from root node A to node B. Node B value is again initialized with alpha is equivalent to minus infinity and beta is equivalent to infinity. Now we move to node D. Again, we initialize the node D value as alpha is equivalent to minus infinity and beta is equivalent to infinity. Node D has two children, namely node H with value 1 and node I with value 4. Now we need to find the value of D. It is maximizing node, so we need to apply max function. The evaluation begins here. Next, it compares node H value 1 with node D value alpha, that is minus infinity, and update the node D value as 1 since it is maximum value. Next, it compares node I value, that is 4, with the current D value, that is 1. Since 4 is larger, node D value is updated as 4 as its final value. This value is then propagated upwards to the parent node B. And the same is updated here in the value of beta. Since node B is minimizing node, we need to update the node D value 4 in beta value of node B. Next, we can move to node E. and initialize node E with values alpha is equivalent to minus infinity and beta is equivalent to 4. Node E has two children, that is node J with value 5 and node K with value 8. Now we need to find the value of node E. Since it is maximizing node, we need to apply max function here. The evaluation begins here. The algorithm first compares node J value 5 with the node E initial value, that is minus infinity. Now it updates node E value as 5 since 5 is maximum here. In node E, we can check that the alpha value is greater than or equivalent to beta. Yes, alpha value is greater than beta, that is node E's alpha value is 5 and beta value is 4. It is true. Since it is true, the right successor of node E, that is node K, is pruned here. And node E value is updated as 5 as its final value. This value is backpropagated to parent node B for further evaluation. Now we need to update node B value. Since node B is minimizing node, we need to update node B with min function and update the beta value here. Since node D value is 4 and node E value is 5, the node B value is updated with value 4 as its final value, since it is a minimum value. The beta value is already 4, so we can have it as such. Next, we backtrack to node A. We need to update alpha and beta values of node A. Since it is maximizing node, we need to update beta value 4 in node A's alpha value. From node A, we move to node C, and it is initialized with alpha is equivalent to 4 and beta is equivalent to infinity. From node C, we move to node F. It is initialized with alpha is equivalent to 4 and beta is equivalent to infinity. And node F has two children, that is node L with value 0 and node M with value 1. Now we need to find the value of node F. As it is maximizing node, we need to apply max function here. Here, node L value, that is 0, is compared with alpha value. Since 0 is less than alpha, alpha value is not updated. Similarly, node M value 1 is compared with alpha value 4. Since 1 is less than 4, that is alpha value is not updated here. But node F value is updated by comparing node L value 0 with node M value 1. Since 1 is maximum, it is updated as final value of node F. Now we backtrack to node C. In node C, we need to update the beta value first. The beta value is updated from node F value, that is 1. So we can see here the beta value is updated by 1 in node C. Now we need to check the condition alpha is greater than or equivalent to B. Yes, alpha value is 4 and beta value is 1. So the condition is true. Now the right successor of node C, that is node G, is completely pruned here. So we no need to traverse the further nodes in node C. Next, the value of node C is to be updated. Since it is a minimizing function, we need to use min function here between the node F and G. Since we have pruned the node G, the node value of F, that is 1, is updated to the node C as its final value. Now we backtrack to node A. Since node A is maximizing node, we need to update the alpha value. The alpha value of node A is 4 is compared with the node C value 1. Since 4 is maximum, there is no change in alpha value in node A. Next, we need to update the node A value. Since it is maximizing node, we need to use max function here between the nodes B and C. The value of node B is 4 and the value of node C is 1. Since B has the maximum value, that is 4, the value 4 is updated to the node A. So finally, the optimal path is from A to B, B to D, D to I with final value 4. So this is the optimal move using alpha beta pruning algorithm. So hope you are clear in alpha beta pruning algorithm with this example problem. Now let's check out the properties of alpha beta pruning algorithm. So the first comes completeness. Yes, it finds a solution if one exists, like mini-max algorithm with few evaluations. Optimality, it always ensures the best move if both place optimally. Time complexity, here the best case is order of b to the power of d by 2 versus order of b to the power of d in the case of minimax algorithm. We can see the difference here. It is b to the power of d, whereas here it is b to the power of d by 2, where b is branch and d is depth. In space complexity, it uses only the order of b into d, but the pruning reduces the storage. Efficiency, it proves unnecessary branches and saves the time. Move ordering, it performs better if good moves are evaluated first. The game type, it is suitable for deterministic zero-sum games and two-player games. Here no learning happens since it evaluates only the current state without past learning. Thank you all.